Let's talk about our first colligative property, which is going to be how solutes affect the vapor pressure of a solvent. And since most of our solvent in general chemistry happens to be water, that's the one we're going to focus on here. So remember that back in Gen Chem when we talked about vapor pressure as a property of liquids, remember that vapor pressure increases with temperature. So as your temperature increases, your vapor pressure increases. Remember that vapor pressure is the amount of gas phase particles of your solvent that are floating above your solution. And so the more temperature you have in the system, the more energy the molecules have, the more likely they are to be able to break free from their intermolecular forces and join the gas phase. And we recall that the boiling point of a particular liquid is defined at where the vapor pressure is equal to 1 atmosphere. And so for water, of course, we know the boiling point is 100 degrees Celsius, and we know that therefore that would be 1 atmosphere of vapor pressure. But we're going to see we have a whole table of vapor pressures. I'll put this table in Discord for you, where you can see how the temperature of your water affects the vapor pressure. In these cases, the units here are torr, or millimeters of mercury. You can see there at 100 at the very bottom. That's when it's 760. But we can evaluate the vapor pressure at a particular temperature, and we're going to actually be able to see how solutes interact with that. And we're going to see that, in fact, there is a very nice direct relationship between the amount of solvent and how your vapor pressure changes. Remember, the point of the result of adding a solute to water, you are essentially adding new intermolecular forces into the equation. So as soon as you add salt or ethanol or glucose, ethanol is a bad example, but glucose, sucrose, calcium chloride, you're adding new intermolecular forces, whether those are hydrogen bonds within new molecules, whether those are dipole interactions, whether those are ion-dipole interactions. You're adding new IMFs, intermolecular forces, into the mix. And we know that, therefore, it's going to take more energy to break those. And we're going to see that if we consider what vapor pressure meant, remember that at a certain temperature, here's our water in here, we have a few molecules in the gas phase, and they're exerting a vapor pressure, right? As soon as we start adding a solute into the mix, remember that the molecules of liquid are only able to escape into gas phase because they've broken free of their intermolecular forces. But now, if we throw in a solute, whether that is ionic or covalent solute, we're going to end up having fewer molecules in the gas phase. So, because the water molecules, we'll say, are attracted to the solute, then it's going to take more energy or more temperature, as we remember that temperature is a measure of kinetic energy. It's going to take more temperature to break free. It's going to take more energy to break into the gas phase. So in order to escape from the rest of the water molecules to the gas phase, it's going to take a higher temperature in order to get the same vapor pressure. And so we can kind of mathematically describe this as saying, well, at a given temperature, if we add a solute to our water, we're going to lower its vapor pressure because we're making it such that there's a higher energy barrier that molecules need in order to escape into the gas phase. And so we can describe this mathematically by looking at the pressure of the solution, the vapor pressure of the solution, that is. First, we're going to look at the pure solvent vapor pressure times the mole fraction of the solvent. And so we're going to see that if our mole fraction of the solvent goes down, remember that this one here, our kind of pure vapor pressure, that's constant. That's something that we'll get from the table that I showed previously. And so we're going to see that the mole fraction of the solvent multiplied by the normal vapor pressure at that temperature will give us our new vapor pressure. And so if we take an example, let's say we have 200 grams of water and 100 grams of, what's a good one? How about sucrose? What's also important here, by the way, the solute must be what's called non-volatile. Otherwise, we're going to get into a whole mess of things that we're going to cover in organic chemistry when we talk about two volatile particles. Non-volatile means it has no vapor pressure by itself. So sucrose doesn't have vapor pressure because sucrose is a solid at room temperature, right? So we're not expecting there to be gas particles in glucose, or sucrose rather. So this relationship only is applicable when your solute is non-volatile, meaning there's no vapor pressure associated with the solute. If you're talking about boiling vodka, for example, that's going to be a whole different matter because ethanol has a vapor pressure that is higher than water. So it's not going to work for that sort of comparison. But for something like sucrose or calcium chloride or another ionic compound, we're going to see that this relationship will hold. So in order to do this, we also need a temperature. Let's say 35 degrees Celsius. Let's figure out what the vapor pressure of the solution will be. First thing we need to do is we can look up the vapor pressure of the solvent at 35 degrees Celsius. If we do so, we'll see that normally we're looking at 42.2. According to this table, it's right here. We can see 35 degrees Celsius, 42.2 millimeters of mercury. All right, so our P for the solvent, we often put standard, that little 0 at the top to indicate standard conditions. We saw that it was 42.2 millimeters of mercury. So we've got that. We've looked that up on the table. We now have to figure out our mole fraction of the solvent. Remember that mole fraction is the proportion, essentially the mass percent, except using moles instead. So it's the moles of whatever we're looking at over the total moles. So if we're looking at the mole fraction of the solvent, we're looking at how many moles of solvent in how many moles of solution. So since this was water, that's 18.02 grams per mole. For the sucrose, 11, that's a molar mass of 342, if I remember correctly. We'll just assume that I'm right, as always. And boom, calculate. Let's do it. 200 divided by 18.02, 11.09877. And for the sucrose, 0.292396, whatever. Remember that mole fraction in this case will be our water with 3 sig figs. These are all moles. Over the sum of the two, plus 0.2923976, also with 3 sig figs. And so if we go ahead and add these together, plus 11.098779913, inverse that. Where's my inverse button? Ah, there it is. Okay, and we're going to have 11.09877 on top. And so we get 0.9743. Again, we're going to have our 3 sig figs there. Now looking at the actual problem, remember that the vapor pressure of the solution will be equal to that of the pure solvent times the mole fraction of the solvent. So the vapor pressure of our solution will be 42.2 millimeters of mercury. That's the from the data table, times this 0.9743. That doesn't have any units. Remember that mole fraction is a unitless quantity. And so we just need to multiply this number by 42.2, and we get 41.1. And so, as expected, the vapor pressure has gone down because we now have fewer solvent particles that are able to escape because they're more now attracted to the solute. So new interactions, harder to break, higher temperature will be required to get them out. And so at this particular temperature, we're expecting it to, the vapor pressure to decrease to 41.1. And so this can be done at any temperature, and we can do it any manner of times with a whole different bunch of solutes. Before we end this video, one more way of looking at this, we can also say that the change in vapor pressure could also be related to the solute instead. We can say it's the pure vapor pressure of the solvent multiplied by the mole fraction of the solute. And that would give us the change in vapor pressure. So just be aware you can use this formula as well. These are both combined called Raoult's law. But you do not need to know that. I will never make you memorize names of things like this, but this is just if I refer to it, or if you see it in a homework problem, this is Raoult's law. It's relating the mole fraction to the vapor pressure. All right, and that's it for this one. We'll next take a look at some more colligative properties.